So far, we've looked at the dependence of a reaction rate on its concentration. And we've been able to see that, especially for our second order reactions, that reaction rate is really going to depend on that initial concentration. So now I'm going to turn and look at the effective temperature on reaction rates. And for this series of lectures, we're going to focus on the Arrhenius equation. But before we talk about that, we're going to talk about just reaction dynamics a little bit more and just collision theory. Uh, so this is a reaction diagram. This is kind of our basic one. It's actually for an exothermic reaction. And what it's really showing here is the energy of our reactants plotted over what we sometimes call a reaction coordinate or time. And the important thing is it's showing the relative energies of reactants versus products. And in this case, our products are at a lower energy, which means that they're more stable and that this would then be an exothermic reaction. And we talked about this a bit with thermochemistry. And that difference between these two, that is our enthalpy right here. And so we would have a negative enthalpy for this reaction. This is kind of showing how the energetics work for a reactant becoming a product. And we're going to focus now on the activation barrier or the activation energy, which is this piece right here. So as our reactants become products, we need to break bonds and form new ones. And so when we reach this top right here, this is going to be the highest energy that the reaction has to overcome. And it's going to be when our reactions or the bonds that are breaking, the bonds that are forming are half broken and half formed. And so this is a very unstable position right here. And so when we look at the temperature dependence of reaction rates, we're really going to be looking at quite a bit at this activation energy. So let's talk a bit about what happens in a reaction. And this is collision theory, something we talked about when we were discussing gases and gas reactions. So collision theory is stating that for a reaction to take place, the reacting molecules need to collide with each other. That we're really thinking about two atoms or molecules actually bumping into each other for a reaction to take place. And so the question is when these two collide is do they collide with enough kinetic energy that can be transformed into potential energy to break the bonds to make the chemical transformation take place? And so thinking about this, we have we start with our two molecules right here coming in towards each other. And as they come towards each other, our kinetic energy decreases and the potential energy increases until they collide. And that kinetic energy is completely transformed into potential energy right here. So now that they've collided, the question is that combined kinetic energy, so the kinetic energy brought by both particles, enough to overcome the activation energy? So if that combined kinetic energy that has now been transformed into potential energy is greater than the activation energy, then we'll be able to see bonds break and bonds form and form products. And if it's not, then they just bounce off each other and nothing happens other than the collision. And then the two particles either transformed into products or still reactants go apart and leave again with kinetic energy bouncing off of one another. And so this is collision theory. And what it means is that for a reaction to actually take place, the reacting molecules are going to collide with each other, but they have to collide with each other in the right orientation to form the new bonds. And they have to collide with enough kinetic energy to make bonds break and bonds form to overcome that activation energy that we're going to call a transition state too. And so there's a lot that needs to kind of go just right for a chemical reaction to occur, for products to actually form. You need the right orientation and you need enough energy. And so here I'm showing kind of two molecules colliding. We have this hydroxide molecule colliding with this carbon with three hydrogens and a bromine. And if it collides in the right orientation, so if it collides here on and hits this carbon on the other side of the bromine, then it is set up to line its orbitals up to form new bonds with the carbon. But if it came in and collided towards the hydrogen, it wouldn't form a bond, right? Its orbitals wouldn't line up with the carbon orbitals that could create a new bond. Or if it collided in here towards the bromine, it wouldn't work either. So it has to come in at the right orientation. So we also need the collisions to have enough kinetic energy, and we see that if we have more collisions with more kinetic energy, so we can call these effective collisions. How about that? If the number of effective collisions, so they have the right orientation and they have enough kinetic energy, increase, then we'll see the rate of the reaction increase. Because if we have those two things that we need for the products to form, the more of those collisions that are occurring, the more we'll actually see products form and the rate will increase. And so that enough kinetic energy can be dictated by temperature, right? Kinetic energy is proportional to the average temperature of the compounds. But we're going to get into the details of how that temperature dependence plays out with the reaction rate constant here. So our rate constant, lowercase k from our lowercase k from our rate law, we find is actually temperature dependent. And so we see this temperature dependence play out in K rather than in concentration. And so it's going to increase as temperature increases. So here's actually what K equals. And so we've been finding this algebraically from experimental data, but K is equal to a frequency factor, which is A, times an exponential factor, which has a lot of fun things in it. It's E to the negative activation energy divided by R, our constant, times T. And so we see that activation energy and temperature dependence in our K expression. And so that's where that relationship where we see K increases, T increases. R for this equation is the version that is 8.314 joules per mole Kelvin. So using our units that include energy. And that frequency factor is going to be equal to the rate that the reactant energy approaches the activation energy. So it's like, how often does two colliding molecules approach the activation energy, have enough kinetic energy to overcome it? And again, the activation energy, I don't know why there's an I there, is really that minimum amount of energy that's needed to break and form the bonds to achieve a transition state where the bonds are partially broken and partially formed. So let's look at each of these a bit more closely. Let's start with the frequency factor. We'll come back to it too later. So this frequency factor A right here is really P and Z. It's really broken up. It's a sum or a product of an orientation factor and collision frequency. So the orientation factor is going to be the number of collisions that have the correct orientation for the products to form. So that means that they're going to collide such that the orbitals will overlap to be able to form a new bond. And the collision frequency, Z, is going to be the collisions per time. This will be dependent on pressure if you're in the gas phase, and it will be dependent on temperature. So we see temperature dependence on Z. As temperature increases, we'll see the number of collisions increase because we have our particles moving faster. And the faster they are, they are going to have more and more collisions with the particles around them and the container they're contained within. So we see that temperature dependence in both the frequency factor, and we'll also see it in the exponential factor as well. So looking at that activation energy in more detail, I've been talking about how these are like half broken, half bonded. And this is actually a really nice demonstration to do in the classroom. And so I don't have it with me, but if I have a nice ruler, I can kind of show this. Maybe I can do it with a pen. So if we have just a molecule that is going to undergo a transformation here, we have a product where our nitrogen is in kind of the middle of this molecule right here, and then it's going to break that single bond and it's going to flip and form a bond between the two carbons instead. And so the activation complex, so the activated complex or transition state, I personally prefer transition state, is going to be the least stable arrangement. And so if it's like this thing is going to be wiggling and wiggling and wiggling and wiggling and have enough wiggle finally to flip, to break the bond and form a new one. And so that's in the transition state, because remember, everything's moving, right? Wiggle, 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 wiggle. It's like when it's here, where it's half formed and half broken, and that it will form products. And so here we use a dashed line or dotted line to show a partially formed and partially broken bond. And so this is showing that it's broken the bond essentially to nitrogen and is going to start forming it to the carbon here in this transition complex. And it basically represents kind of like halfway between the products and the reactants, right? And so that least stable arrangement, that's the one that defines our activation barrier or activation energy. It's because we need to be able to have enough energy in the system of these two particles to be able to create that state of being or matter before it can then finish forming bonds and finish breaking bonds. And so we think of these as having partial bonds. So the frequency factor then is going to represent the number of approaches to that activation barrier over time. And so as this wiggles and wiggles and wiggles, some of the wiggles are going to get really close to partially breaking the bond, but then kind of go back. And so what we see is that only some of them will actually be able to hit that transition state and transform. And so the the frequency factor is just going to track the number of approaches up to that activation barrier. And so the frequency factor is going to represent, in this case, the rate at which the NC part of the molecule, that triple bonded part, vibrates side to side. And so that rate of vibration will be represented in the frequency factor. And this is like kind of a simplified reaction of a kind of a change within a molecule. Some of them, it's going to be the number of collisions that come in at the right orientation with the right energy. Others, it might be stretches rather than like a vibration type motion that leads to the chemical reaction. So our exponential factor was taking into account everything that was e to the, and it was activation energy, R and T. So here's our second kind of place where we have temperature dependence right there. In this case, the exponential factor is really going to be a number between 0 and 1 that's going to represent the fraction of approaches to the activation energy that are successful. So our frequency factor is the number of approaches, and this exponential factor is like the number that are successful and make it to products. And so in this case, we see that even small changes in temperature result in large changes in our exponential factor, because it's basically, here's our activation energy right here. And if when we have a given temperature, right, our molecules will have a distribution of kinetic energies where that temperature is proportional to the average kinetic energy. But as we increase our temperature, we see that average kinetic energy increase, and we also see the distribution broaden. And so as we increase our temperature, so our temperature increases and we go to this red line here, we see that we get all of this all of these more particles. That's a terrible way to say it. We see many more particles have an kinetic energy that's higher than the activation energy. And so that kind of dictates how many of these are going to be successful, all of these approaches up to this activation energy as this particle is vibrating or stretching or colliding. And so as we increase temperature, we increase the average kinetic energy of our particles. We increase the number of particles that have higher kinetic energy than our activation energy, allowing more collisions to produce products.